The next talk is by Paulin.
All right. Hello. Oh, where's the clicker? Perfect. All right. My name is Jillian. I am a PhD student at the University of Pennsylvania. And Rebecca gave me a great introduction before. I have been working on producing Hourglass 2, which is an updated catalog simulation for the Roman Space Telescope High-Latitude Time Domain Survey. So, as I've said, Hourglass 2 is a collection of updated simulations. We're using the most up-to-date observing plans and recommendations, which it means that it's going to be the most realistic catalog simulation as the successor to Hourglass 1 by Ben Rhodes and others in 2025. So we're simulating several transients. Our supernova cosmology pit cares the most about type 1a supernovae, but it's going to be very useful if you're also interested in core collapse or rare transients, including parainstability, ILOTs, kilonovae, TDEs, superluminous supernovae, 1AXs, and 1A91 BGs. There are also AGNs as part of this catalog if you're interested in those. There will also be light curve fitting analysis using the SALT-3 light curve fitter, as well as classification, training, and testing with the SCONE supernova classifier, although I will not be really touching on either of those in this talk. So these simulations were produced with the supernova simulation software SNANA and the Pippin wrapper. So Rebecca already introduced the survey design, but as a quick recap, there are three main components: the pilot component. There will be 8 pilot epochs, which are divided between a couple template and a couple science epochs. And that's going to take place over the course of 115 days, evenly spaced at the start of the survey. There's the extended component. 3 of those epochs will be between the pilot and the core, and they'll wrap up after the core. The major component of HLTDS is the core. That will take place over the course of 2 years. And that has the 5-day cadence that's been advertised so nice. So we're going to get really, really beautiful light curves during that portion of the survey. And the extended component of the survey will help us to follow up those highest redshift transients where we're seeing a bit of time dilation effects. So these are what the survey footprints look like. There are 3 major fields, technically 4 maybe, on the all the way on the left here. These are the north fields. You can see this ring of overlap. The wider area is the wide tier of the survey, and it's circling around the deep tier of the survey. So there is a little bit of overlap region, which is pretty cool. And then the south fields, there is a deep field, which is smaller than the wide field. And the deep field will also have spectra taken there. All right, so what is the difference between the wide and the deep tiers? The wide tier is useful for capturing more transients with some lower redshift filters. And the deep tier will be useful for capturing transients at higher redshifts with longer exposure times. In addition, spectra, as I mentioned, will be taken in the south deep field. And we can also break down, the spectra has their own wide and deep tiers, longer exposure times, et cetera, et cetera. So this is a count of all of the different transients that we can expect to see given this survey. Over the course of the entire survey, we can find 31,111 type 1As, which is crazy. That's a really big sample. There will be over almost 45,000 core collapse supernovae and quite a few 91 BGs, 1AXs, et cetera, and a few of those rare transients as well. This is the redshift distributions for all of the transients in this survey. On the left, I have the more common supernova 1As and core collapse. So the nice thing about Roman is that we are reaching these really high redshift supernovae, which we haven't really probed before. And the rare transients are shown on the right here. And yeah, we are also expect to see quite a large number of core collapse supernovae throughout the survey. So as we mentioned, we care a lot about how we can use type 1a supernovae to probe cosmology. So I'm going to zoom in on those for a bit. So we have a lot of supernovae, but how good are they? This is the same redshift distribution that I've shown you before, but I divided it between wide and deep tiers, and I've color-coded it based on the SNR based on the light curves that I simulated. So for cosmology, we typically want an SNR 30, 40 to be on the conservative side. And there's still a very large number of transients that do get out into those really nice high redshift areas, especially in the deep tier. Here are a few example light curves from my simulations. I've picked completely at random type 1As from the pilot, core, and extended. Really, I just wanted to illustrate what the cadence looks like in practice. And again, for pilot, since that's more for templates, we're not really expecting beautiful light curves, but look how nice the core light curve looks. It's very, very well defined. We can see the second bump. Beautiful. And the extended, I've on purpose randomly selected a light curve that has some data from the core where it's more concentrated, and then there's some follow-up data from the extended component there. So when we care about doing the cosmological analysis, we want to throw away garbage, light curves that are not as high quality as we would like in order to perform cosmology. So this is the same redshift distribution again. In purple, that's all of the supernovae, the type 1As that we expect to see. And then I isolate just those that would be useful to perform cosmological analysis. So those cuts are, we want at least one light curve data point before the peak. We want at least one data point within 5 days of the peak, at least 1 point more than 2 days after the peak, and at least 30 or more days after the peak. That way we can see the tail end of these supernovae. So as I've mentioned before, we have over 31,000 before these cuts, but we're still left with a nice large sample after these cuts, 15,433. So I'll briefly touch on the classification that we can do. We can train and test using SCONE. And this is just the confusion matrix representing how well it's working. It works pretty great. The non-1As are identified as non-1As. 1As are properly identified as 1As. So in conclusion, I am working actively on this paper. It should be out soon. So look out for a paper called Hourglass 2. It uses the most up-to-date survey plans and recommendations. So all of this data will be publicly available. And that includes light curves, that includes spectra, and you can use it for a wide variety of applications, not just cosmology. We also will be releasing the light curve thinning and the classification results if you're interested in those as well. So the next steps is to actually perform these cosmology analyses with this data. So I would like to acknowledge all of these people. Masao is my advisor, Rick Kessler, Ben Rose, Cole, and Rebecca, who are here for all of their support and help throughout this project, as well as the entire Roman SM pit. So, questions?
Thank you, Gillian. Any questions? Yes.
Thank you for the nice talk. I'm looking forward to seeing the simulations. I was just curious where you're getting your redshifts from.
Where we're getting the redshifts from?
For the type 1As?
For the type 1As? Rebecca, do you want to?
Rebecca.
Within the SNN simulations, we have rate equations that we put in there, and then it does like volumetric rates within that. And so that's how we kind of get the redshifts and the number of supernovae, things like that. But do you mean like how we're, you mean how we get them from?
Yeah.
Okay. So we'll use a combination of the prism spectra, as we talked about previously in the pit talk. We'll also use spectra from other facilities like Subaru, for instance. And then for the light curves, we'll have, we might use photoz's or things like that as well. There's been a lot of work that's been done by Bob and Jarsi on photo-Z work and using data from Roman and Ruben for that purpose as well. So yes.
Thanks.
Any other questions? I heard the voice somewhere. No? Go for it.
I was wondering for the sort of rate estimates you made for some of the rarer things like the ILOTs. I'm interested in these like red, dusty, rare transients. So I was wondering what kind of templates or rate assumptions went into those calculations.
Ooh, the rate assumptions is a good question. Yeah, I'm not sure off the top of my head, but these are the models that we use for those transients.
Mhm.
Probably doesn't answer your question.
That's okay. I mean, I can look at the paper too, but thanks.
Any other questions? If not, I'll ask a question about this slide. So you're simulating both supernova, but also other types of transients, and you're treating them as contaminants. These go also into the classifier confusion matrix that you showed? Like
Yeah,
contamination?
so one caveat for my confusion matrix is, this, so these it includes all of the contaminants. And actually, I did include a little bit of garbage, so this can only get better in the final product.
Yes.
Up to 3, yeah. Yep.
Yes.
I'm sorry, I just wanted to clarify that these go out to quite a high redshift, so up to at least redshift 2, as I understand it. So
2.9.
2.0. So, and with Scone's classifier, which I believe is what you're indicating here, we're getting good classifications between non-1A, 1As, and the subtyping of things as well, as I understand it.
Yes.
Great, thank you so much.
Thank you. Any last questions? Okay, let's thank Jillian again.